So we're going to continue to talk about some applications of integrations, but I just wanted to give you sort of a summary of everything we've done so far with integration. So we've talked about approximation with rectangles, rules for integration, definite integration, integration by use substitution, both indefinite and definite, and also integration by parts, indefinite and definite. And then we talked about the applications in kinematics. So now we want to look at the concept of finding the area between two curves. So to do that, we just look at an example graph. I just put up these functions. It's x cubed minus 3x plus 3 and x is the square root of x plus 3. That's what the two of them are. So g of x is the x cubed one, and this is the square root of x plus 3. But it doesn't really matter what they are. You can see that there's a space in between them that I've colored in blue. That's the area that I want. And so the question is, how do I find that area? And essentially what the process is that's involved in this is a fairly obvious one, I think. You just find, if I find the area, I sort of go as straight a line as I can. If I find all of this area, which is the area under f of x, and then I say I'm going to take away this area, which is the area under g, I should end up with the blue area. Okay, so visually you can kind of see that makes sense. Mathematically, this is what we say. If we want the area bounded by those two curves, we find the area bounded by the top function, that is the function that's greater, and we find the area that's bounded by the bottom function, and then we subtract them. Now, this only works if the boundary is the x-axis, in terms of they're not down below, because sometimes then the top function, the bottom function are going to change. So we have to be careful with what our boundaries are. So what we're saying is it works if it's non-negative, in the sense that we can't subtract them if one is going to be negative, because then it's negative area if it's underneath the x-axis, if that makes sense. So we have to be careful with signs. But when we find the area between the two curves, if we take the top function minus the bottom function, and keep in mind that we need to have positive area minus positive area, we're assuming that both areas are positive, then we get this as our mathematical statement. So the area is the integral from a to b of f of x minus g of x dx. And both f and g of x are continuous functions. That is, you can integrate them because they don't have breaks in them and they don't have holes in them and those sort of things. And the function f is bigger than the function g all the way through the interval. Now, if it's not, we have to correct that. We have to correct the interval, or we have to change the top and bottom function. We'll talk more about that. But that's essentially the idea. So what we have to do in terms of evaluating this, how do we do this? The first thing we have to do when we're given these two functions is to draw a picture. Draw a picture of what's happening. And then what I'm suggesting is you draw a vertical line through the region to try to figure out what the top and the bottom boundaries are. You can also, you don't need to do that. You can just look at the function, and if you can visually see that the f of x is the top one, so you have to find what that is, and the bottom one is g of x, we have to find what that is. All right? And then f of x minus g of x becomes our integrand. And then the limits, you just have to figure out, again, if you're moving that line, that vertical line that we've created, back and forth until it goes from one of the intersection points to the other. So sometimes the question is going to give you the intersection points. The other option is that you have to find them yourself by setting the two functions equal. So that's what I've said there at the end. The limits are sometimes given, and sometimes they're left for you to find. And then once you have the integral, you just have to evaluate it. Most of the time, you can do that with a calculator or some other computer program, because you don't have to do the algebra and plug numbers in and do all of that numerical calculation either, but you have to be able to set up the integral and say this is what the area is going to be represented by. So just give you a couple of examples of that. Here's an example. It says find the area bounded by y equals x squared, y equals x cubed in the lines 1 and 2. So the first thing I do is I draw in x squared, and that's my parabola. And you should know or have some concept of what that looks like. Then we're going to draw an x cubed, which is that sort of snake look to it. So it kind of comes down, bends, and goes back down. And then it says the lines x equals 1 and x equals 2. So there's x equals 1, there's x equals 2. And so then I just shade in. That's the area I'm talking about. I want that area. So what the suggestion is in terms of the steps I just wrote down is to draw a vertical line. So there's my vertical line, and look at what's the top of that. The top of that is x cubed. And then what's the bottom of that? X squared. And then the idea is move it along here, and you hit x equals 1, and move it up until you hit x equals 2, and that's where it stops. So your boundaries are 1 and 2. Those aren't the intersections of x cubed and x squared, but they are the intersections because they say the area is bounded by 1 and 2. All right, so that means that our area becomes this. So we're going from 1 to 2. Those are our two boundary limits, the lower limit and the upper limit. And then the functions are x cubed minus x squared, because that's the top function, that's the bottom function. And at this point, then you can integrate and plug your numbers in. You either do that algebraically, like I've done here. So you plug in 1 and 2 into the integral of x cubed is x to the 4 over 4, and the integral of x squared is x cubed over 3. And then you work your way down, and you get those values, and then you get a common denominator, and all the way down you get 17 over 12. Okay, and I'm confident that if you've done integration up to this point, that is not the difficult part of this. But you also can use a calculator generally to do this, so that you don't have to worry about messing that up. You can just type it into your calculator. All right, so here's another example. Find the area between x plus 6, x squared, and then 0 to 2. So again, you have to draw the picture. You can use your calculator generally to draw the picture if it's not given to you. Sometimes it is. Or you can just give a rough sketch based on your knowledge of functions. So you should know that x plus 6 is a line. It has an a y-intercept of 6, and it has a slope of 1. So it's going to be like that, right? It's going to kind of go along, assuming that that's 6 there. And this is a sketch, so I haven't put a scale. And then y equals x squared, we're kind of going like that. And the parabola continues out here, but I've drawn it only from here because it says this, it's bounded by x equals 0. You could draw in there on the other side as well. It's going to come up and it's going to hit somewhere over there. And this, if this continues, so you'd have another intersection point right there, and you have an intersection point right here. But this doesn't tell us to use those two intersection points. It says find the area bounded by 0 and by 2. All right, so that's what I've done. I've drawn in 0 and 2. I have to then look at what is my top function. My top function is the line. You can see that, right? Again, if you want to draw your vertical line, you can. So the top function is x plus 6. The bottom function is x squared, and that is the case all the way through here, right? All the way along. That doesn't change. So my area becomes this. And again, that integrand is really in brackets. We're taking the integral of this whole thing. And again, once you've set it up, your boundaries are 0 to 2, you've got your integrand, then you can just ask your calculator to find it generally, or again, if you want to, or if you don't have a calculator that does it for you, you can work it out. And so you integrate x squared over 2 plus 6x minus x cubed over 3, you plug in 2 and you plug in 0. Plugging in 0 results in 0 because all of these x's would be 0. So we'll just plug in 2 and figure out what that gives me. And there's my answer. It's 34 over 3. All right, so if you use your calculator to do it, you just get that answer probably as a decimal, so you might have to ask your calculator to do it by converting it to a fraction afterwards. All right, now, if we go on to the next one, I just want to show you, this is very similar in that it asks you to do the same thing. It says find the area enclosed by the two curves we just talked about, y equals x squared and y equals x plus 6, but it doesn't say between 0 and 2. And so what you have to do then is you have to figure out the integrand's the same, because x plus 6, if you look at your picture, and I've drawn the picture here with a computer program, x plus 6 is still bigger the whole time. So x squared is the bottom function the whole time. But I need to figure out what are those points. Now you can look on your graph, if you've drawn it with a calculator, or with a computer program like I have, you can see they're -2 and they're 3. But if you're not sure, or you want to make sure, you can set the two functions equal to each other. So I get x squared equals x plus 6. That means I slide everything to the left-hand side, and then it does factor. So I'm solving my quadratic, and I get my two answers. So all that changes is my integral, my area now is from -2 to 3, same integrand, x plus 6 minus x squared. And then, again, you integrate that, and we won't take time to do that on the video. I'm confident that you know how to do that, but that would be your integral. So there's two sort of options. You're either going to be told, here are the boundaries, or you're going to have to find them. All right? The last thing you might have to do is you may be given a question that has to do with relations. So x equals y squared and y equals x minus 2. So when I look at that, I have to figure out, how do I draw that picture? And the way that you draw it is you can solve this for y, okay, and you're going to get this picture. Now I'm going to just erase all the area, but that's y squared, x equals y squared is a sideways parabola, and this is our line y equals x minus 2. And you notice this is the area that I'm talking about. We had it shaded before, but I'll shade it in now. You can kind of see that's the area I'm talking about. What's interesting about this is that this is solved for x, and we can solve this for x fairly easily. We can make it x equals y plus 2. And so instead of doing it in terms of x, we're going to do it in terms of y. So to do that, we draw a horizontal line instead of a vertical line, and we look at front function minus back function. Okay, now can we do it with respect to x? Yes, we can. But if we do it with respect to x, it gets more complicated, because if you notice, if we're doing it with respect to x, you have a line here. The top function is plus root x, the bottom function is minus root x. But after this point, you now have a different bottom function. So if you do it with respect to x, what ends up happening is you get your intersection points are 1 and 4, okay, setting those two functions equal to each other. But you have to split your integral. The first part of the integral from 0 to 1, so that's this part here, all of this. The top function is root x, the bottom function is minus root x. So that's where I'm getting this from, okay? But then from 1 to 4, the bottom function is now the line, x minus 2. So you get a fairly complicated integral. If you do it in terms of y, you instead get the intersection in terms of y. So y squared equals y plus 2, and you get minus 1 and 2. Your front function here is the line. The line is x equals y plus 2. So we're going to use y plus 2 as our front function, and the back function is x equals y squared. And I'm saying front and back because we're talking horizontal. But you notice they stay the same all the way along. So if I take that horizontal line and I move it anywhere along here, the front function is y plus 2, the back function is y squared. So that leaves me with an integral. It's with respect to y, not x, but the area is only one integral, okay? So it's from minus 1 to 2 of the front function, y plus 2, minus the back function, y squared. So you have the option of deciding which of those you want to do. And I'll leave that there. We'll practice.